Before seeing Bourgain's proof, we're going to consider a few examples. As a first example, suppose that our distance function is as follows. There's a graph G, which is just a cycle, and distances between vertices u and v are just the length of the shortest path in the cycle between u and v. And now suppose that we pick a random set A in the following way. First, we pick a random vertex, and then we set A to be the singleton, which is just that vertex. Then we define fa of u to be just the distance between u and A. Now, what is the expectation over the random choice of A of fau minus fav? But this is a calculation that you should try to do, and you can see that this expectation up to a constant factor is proportional to the actual distance in the cycle between u and v. So in this example, picking set A to be just a random singleton works very well. In other cases, however, this doesn't work well at all. So suppose, for example, that all the distances are the same. So we have a distance function such that duv is 1 when u is different from v, and duv is 0 when u and v are the same vertex. And suppose again that we pick a random vertex, and then we define the set A to be the singleton that only contains A. Then fa of a vertex v will be 1 if v is different from A, and 0 if v is equal to A. Then what is the expectation of this difference? Well, this is going to be at most 2 over n, because except with probability 2 over n, A is neither u nor v, in which case this difference is 0. When A is either u or v, then this difference is 1. However, in order to prove something like Bourgain's theorem, we would need this expectation to be much larger. This will still be easy to fix by noting the fact that we want all distances to be the same, and actually those expectations are all the same. So after multiplying f by n, we actually get what we want. But here is an example where picking just a random element does not work. Suppose that there are two sets, S and V minus S, and our distance D is defined so that the distance is very small, let's say 1 over n, if U and V both belong to S. And it's also very small if neither of them belong to S. So if they're both in V minus S. But the distance is much larger, let's say it's 1, if U is in S and V is not in S, or vice versa. Now when we look at the expectation over A of FAU minus FAV, say U and V are both in S, this will be 0 except when A is either U or V, in which case it will be 1 over n. So this is roughly 2 over n squared, much smaller than the actual distance. And in this case, it doesn't work to just scale up the value of f, because when we look at this expectation where U is in S and V is not in S, this will be at least 1 minus 1 over n, because for every choice of A, either FU A will be 1 over n and FAV will be 1, or vice versa. Or possibly one of them could be 0 and the other one will be 1. So that contributes an extra 1 over n squared to the expectation. So in this case, the expectation is very close to the actual distance. And here the expectation is a factor of n smaller. So it's impossible to make, even after scaling, to make the expectation be within, say, a log n factor from the actual distance. Now let's suppose instead that A was chosen uniformly at random among all subsets of V, so that every vertex belongs to A with pretty half independently of all the other vertices. So let's see what's happening if instead of picking a very small A that only contains one element, we pick a large A that on average will contain n over 2 elements. Then this works okay for two elements that belong to the same cluster. For example, if U and V both belong to S, well, we can see that A is going to include some random subset of S and also some random subset of V minus S. So when we look at U and V, there are going to be 4 possibilities. Either A contains V but not U. In this case, FAV is 0, but FAU is 1 over n. So the difference is 1 over n. And the same will happen if A contains U but does not contain V. Because then FAU will be 0, FAV will be 1 over n. The difference will be 1 over n also. But if A contains both U and V, or if A contains neither of U and V, then the difference will be 0. But one of those two cases happens with probability half. Each of them happens with probability 1/4. So this expectation will be at least 1/4 times 1 over n, which is within a constant factor of what we would like. Unfortunately, this expectation does not work when U is in S and V is not in S. Because let's say those two sets, S and V minus S, have about the same size, then except with exponentially small probability, A will intersect both S and V minus S. So both of those numbers will be between 0 and 1 over n. And this is terrible because we would like the expectation to be actually close to 1. So here we have an error of a factor of n. But then if instead we pick A to be a random element of V, and then the set to be just the singleton A, this distance for elements that are in different clusters now suddenly works, because the set A is just one element. That element is either in S, which makes FA of V be 1, and FA of U to be either 0 or 1 over n, or vice versa. So then in either case, we're going to have this to be at least 1 minus 1 over n, which is great. He's very close to 1. But as we saw before, picking A to be a singleton doesn't work for distances between elements that are in the same cluster. So the way we resolve this problem is to just mix the two distributions. So we're going to say with probability half, we pick A to be a singleton, and with probability half, we pick A to be a random subset. The calculation that we did before, the picking A uniformly works for distances of elements within the same cluster. It's a calculation that still holds after losing a factor of 2. And the expectation we computed that said that if we pick A to be a singleton, we have a good expectation for distances of vertices in different clusters. It's again a calculation that still works after losing a factor of 2. So this mixed distribution will work both for elements in the same clusters and for elements in different clusters.